I'm sure most people in the department know me. I've been lecturing here in the computer science department for the last 23 years as of last month. And for the last 8 years, I've been working on a PhD under the supervision of Professor Cormac Strinan of University College Cork. 8 years part-time, of course. The theme of my research is the management of software-defined data center networks. And in this presentation, I just want to give an overview of some of the work that I've been doing on that. A bit of background first. Well, I'll assume that everyone knows what a data center is. And of course, a data center network is the network in a data center. And this work is done, the work that I've been doing is in the context of that environment. A data center network where you might have maybe hundreds of switches, thousands of hosts, possibly up to that level. Well, in a multi-tenant data center network, tenants can arrive, change their requirements, and leave as well. It's a highly dynamic environment. And a multi-tenant data center network, it's a natural candidate for software control, where you programmatically control the use of resources. And an OpenFlow controller is one option there. OpenFlow, it's a protocol, and it has the benefit of being an open protocol. Netconf would be another open alternative, or there are proprietary options as well. But in an OpenFlow network, OpenFlow messages are exchanged between the controller and the switches, some of them to discover the layout of the network topology, or to maintain switch controller relationships, but primarily to keep flow tables on the switches up to date. And the flow tables, that's where the policy of the network is essentially implemented. The flow tables might be updated proactively to correspond with tenant changes, or reactively to correspond with flow arrival and departure. So the motivation for the work that I've been doing is to provide a facility to answer DCN operator queries about the past state of their network, a network whose configuration changes rapidly and continuously. And DCN operators want to know about the behavior of the switches in their network, the controllers, the hosts, and packets for the purposes of maybe auditing and compliance, or verification, troubleshooting, or what-if scenarios. Some questions the DCN operator might find answers useful to these questions: what switches were actually active in the network, and when. They know what switches are physically present, but were they all active? Or if not, when weren't they active? Or even more challenging to answer, for what hosts were flow rules installed in switch flow tables to allow packets to flow from or between those hosts, but no packets were actually observed? And this could reveal a situation where the network policy is out of date. Maybe there's rules in there that aren't required anymore because maybe a tenant left. The DCN operator might want to know what path a packet with certain header fields would have followed through the data center network, and to what destination would it have gone to at a particular time. Well, answering these types of questions requires the state of the network to be recorded, and the network to be modeled somehow so that its state can then be analyzed and queried. So Cormac and myself, my supervisor, we agree a few research questions. Could we passively and accurately capture and record OpenFlow messages from a data center network? How accurately could we reproduce the network just using those messages, reproduce it for the state that it had at any time in its recorded history? And how could we model the network in such a way as to be able to answer queries that would be useful to a DCN operator? And could we formalize a methodology for creating new queries? In a paper that I presented at the Networks of the Future conference a few years ago, I described a system that we implemented to passively capture OpenFlow messages. So from an existing network, and having minimal impact on the operation of that network. Just passively capture the messages and store them, process the messages in the store, to produce snapshots of the network state at time intervals. And using those snapshots and the messages in the message store, reproduce the network quickly for whatever time point is required in the recorded history. And the reproduced network is an emulated copy of the original network with the switches, the hosts, the links, and the flow table contents. We showed how the use of snapshots makes the reproduction time deterministic. And this chart shows how long it would take to reproduce a network for each point in its history without snapshots. And that's the the red line here, recreating a network by processing the OpenFlow messages in the log from the start of the log. So if we needed to recreate the network for 3 minutes into the time in the history, and then that would take 250 seconds. Whereas with snapshots, that time is reduced to something like, if it's 3 minutes, somewhere around 50 seconds. So snapshots provide an upper limit to the length of time that is required to recreate the network. And that upper limit is dependent on the distance or duration between snapshots, measured in time, or really measured in the number of OpenFlow messages between snapshots. And in this case, for the chart produced here, it was 75,000 OpenFlow messages between snapshots. This slide gives an idea of the scale of a reproduced data center network and the kind of size data center network that I was using for my experiments. 12 switches, 120 hosts. Not all of the hosts are shown here. This is, as I said, a reproduced network. And the only information that's used to reproduce the network is the log of OpenFlow messages that were exchanged between switches and the controller in the original network. So if a host wasn't active on the original network for the duration of the capture, I suppose, then it won't be mentioned in OpenFlow messages and we won't know about it. I want to mention here as well the use of MaxiNet, a distributed SDN emulator that's based on the non-distributed MiniNet SDN emulator. So that was fine. Producing a copy of a network is useful. Well, we saw it as being useful to allow a DCN operator to experiment, to review the state of the network as it was at some time in the past, because it might have changed significantly from then to what the state of the network is now. So they could, on the reproduced network, they could look at the contents of the flow tables, they could see what hosts were present, they could check what the path for packets between hosts was. But it was kind of a snapshot still of the network state. And that doesn't make it easy to answer some very interesting queries that a DCN operator might have, particularly queries with temporal parameters to them. So we decided to try to come up with a richer model of data center network, and we took an ontological approach to doing that. So that work then I presented at the IEEE Software Defined Systems Conference just last year. With the ontological approach, well, the reasons for using an ontology, well, I'll come to them, but an ontology formally encodes relationships between concepts. So we had to be able to define the data center network in terms of concepts. And we built a logical framework of those concepts from control plane messages. So we essentially had to define control plane messages. What do they look like? And how can we build a model of the DCN based on that and infer the existence of actual switches and hosts and links and so on in the network through that framework. So the reasons are benefits, I suppose, of the ontological approach were that it would allow us to do consistency checks and correctness checks. We could extend an ontology and enhance it without impacting previously working code. So it can be extended over time, and the ontology can be populated to represent a specific network and then queried, and then it can be cleared out and populated with the messages from another log file, and that log file queried. So it gives us quite a bit of flexibility. Now we built a hierarchy of ontologies, starting with existing ontologies whose authors kindly made them public. One is the network markup language ontology, which describes basic components of a network. An interesting one is the change ontology that describes temporal concepts, not specifically for networks, but for general use. And that allows us to represent changes to instances of concepts over time. So, a switch is a concept, a DCN switch, that's a concept, but a specific DCN switch, it might be an instance of a concept. Well, we came up with an OpenFlow message ontology that describes OpenFlow message types and properties, and that can be populated directly from a message log. And then the DCN history ontology that we defined adds detail to the network markup language's description of network components. It also adds new components or new concepts and leverages then the change ontology to give a temporal dimension to the model of a data center network that's inferred from the populated message ontology. This is just a fragment of the DCN history ontology that describes higher level concepts, elements of DCN like controllers, switches, and hosts. So reading the ontology, just briefly, you can see that a switch concept, a switch has properties like data path identifier that should uniquely identify the switch. It also has a TCP port that it operates on and an IP address that it's identified by. But it has subcomponents. A switch has ports. A switch has one or more flow tables. Well, an OpenFlow switch does. Ports on different switches can be connected to each other via links. The flow tables contain flow rules. So some of these concepts, they're reused from the network markup language ontology. The network markup language is atemporal. It doesn't have any temporal kind of dimension to it. So we use what's called Krieger's 4D approach to add the required temporal aspect to them in our ontology. And that's following the examples in the change ontology. So for example, a flow rule has a perdurant part and a manifestation. And the perdurant is the long-lived part. The properties don't change for the duration of the instance of the flow rule. But a flow rule in the real world can be modified. So some properties stay constant, but others can be modified. And when a flow rule is modified, that's another manifestation of the flow rule. So these terms come from Krieger's 4D approach. And they allow us to represent the changing nature of the data center network. And this, we believe, is the first application of 4D to SDN. So other researchers have made use of ontologies, but there's not much work done on kind of temporal use of ontologies. So, our ontological approach, we had to come up with a workflow, and I've diagrammed it here. The first step is to write the ontology. Can be written by hand because these are text representations, textual representations, but there are tools. Protege is one that's very commonly used that make it easy to graphically create an ontology. The ontology has to be imported into a triple store. Well, Protege will act as a triple store, but we're talking about a data center network with that's highly dynamic. We need a kind of a beefy triple store, and the one we use is Allegrograph. Then the OpenFlow message ontology has to be populated with instances from the message log, the OpenFlow message log, and we use Python scripts for doing that. Most of the implementation work actually went into the inference of DCN element instances, the inference from the OpenFlow messages, inferring switches and the lifespans of the switches and the changes to the switches over time, switches, controllers, hosts, links. Once the concepts and the instances have been inferred, then we can run queries on them, and the queries are written in Lisp and Prolog and Python. So a lot of kind of work there, a lot of implementation work in order to be able to then actually answer some queries. And this chart here, this was produced as part of the work of verifying the approach that we took. And graphically, it's representing a set of switches towards the top of the diagram, at the top of the chart. They're the switches and the links between the switches, and then hosts connected to each switch, 20 hosts connected to each switch, and the data path identifiers of the switches and the IP addresses of the hosts. Now, it's a composite chart that shows all of the devices that were inferred, regardless of their lifespan or of how long they were active on the network, the data center network for. So I just want to do a bit of a sidebar and show you this, my Linux virtual machine, not this chart, not yet, but here. So we're looking at a chart of a network inferred from OpenFlow messages, and that the duration of time for the experiment is divided into time slots, 100 time slots. And I can kind of animate this manually, really, and show within each slot what elements were present. So as time kind of elapses during the experiment, we can see more switches present and being active. They're communicating with the controller. A little bit of time before the hosts become active based on a traffic generator. Now a bunch of hosts have been inferred in slot, well, they started appearing from, looks like slot 35 there. And more hosts becoming active. They're not all active for the same duration of time. Some appear and disappear based on when they were sending traffic and when there were flow rules present to relay their traffic through the network. And it's getting to a point now where a switch actually disappears. And I remember doing this experiment, I was looking to see if I could identify a failed switch. So I actually killed the switch. I terminated it. And all of the hosts that were connected to that switch could no longer be active on the network. As the experiment came to a conclusion, then the remaining hosts became inactive, and gradually then switches started disconnecting from the controller. So this kind of shows the power of the model and helps get across a temporal aspect. And this could be shown as the result of a query. The other chart that I had up there when I went to this Linux machine first, this is the one. This is another view. It's the result of another query of the data, saying, okay, for the switches in the network, and the switches are identified here by data path identifier. When actually were they active? From when to when? So we can see from the start of the experiment, 4 of them were active from that point. They had established communication with the controller. Then another 4 became active and the last 4. And one of them then disappeared before the end of the experiment. And this was the point in time when I killed that. So we see this information as being useful to a data center operator. I'll just go back to the slides now. Yeah, that's a similar chart to the one that I showed you there, but in this one, the switches all remained present until the end of the experiment. So these kind of charts were used to evaluate the accuracy of the model. I gave an example possibly of the kind of query the DCN operator might have, looking to find out what path did a packet follow, or would a packet have followed if it was sent on the network from some source to and intended for some destination at a specific point in time. And here, okay, it's the query. There's some parameters provided as part of the query: the source MAC address, the destination MAC address, and the Ethernet type field value. And that's enough, along with the time at which we want the query to be focused for. That's enough to be able to apply that query. But I just want to make the point that just because the destination is set to be a particular host MAC address doesn't mean that that's where that packet will go to. And we should be able to identify that with the result of a query. So here's the composite chart of the network, and overlaying on that the result of the query. Yeah, from host 10.0.3.1.1 and going to the switch. Yeah, I was just looking for my spotlight there. Going to this switch, which is the switch that host is connected to. Traveling to another switch. Now, there are a few paths that the packet could have taken, but based on the flow rules that were configured on this switch at the point in time of the query that the query is relating to, then the flow rules that were configured will result in the packet being forwarded along this path and getting to this destination host 10.0.4.11, which I think was the actual intended destination. And so that was the work that I presented at Networks of the Future. And the work that I'm doing at the moment, well, I've been extending the ontological model with more high-level abstract concepts in order to be able to answer sophisticated queries. So a concept such as migrated host. So a host in a data center could, if it's a virtual host, it could be migrated to a different part of the data center and running on a different server, a physical server connected to a different switch. So I've defined that concept, the concept of a migrated host, so that I can then answer the question, what hosts did actually migrate in the history of the data center network? Or I've also defined the concept VPLS tunnel, because flow rules can be configured to create tunnels through the network so that packets can be handled efficiently through those tunnels and kind of create an overlay network. So a DCN operator might well want to know, well, what tunnels were configured on the DCN? And having created the concept and written the code to be able to infer instances of that concept, then I can answer the query. I'm also working on the methodology, trying to formalize the process of designing the concepts, developing the concepts, and the inference process and the query design, so that it's straightforward how to make future additions to the ontology. And my primary focus at the moment is to actually finish writing up my PhD thesis. So that's it. That's my presentation. Just wondering, are there any questions?
Thanks for that, Jonathan. That was great. Okay, any questions, anybody?
Hi, Jonathan. Dylan here.
Oh, hi, Dylan.
I've heard you speak about this a couple of times. I absolutely, I'm fascinated by it every time that you
thanks.
you bring it up. I love
I'm
looking at it.
I'm just happy when people are still awake at the end.
It's very nice because you have a web page there where you actually have an application where you can actually show what's going on. It's fantastic. What I was wondering was, so like again, I've heard you speak about this before, so I might have brought this up in the past, but this seems fantastic for troubleshooting, kind of like what you were talking about. But it seems like something that would be very useful for security in terms of forensics, or in terms of malware analysis as well, because you could have a fake network basically created and allow the malware to run and then just kind of track what happens. But what I was kind of wondering, then based off that, is how much data is actually generated for this, or how much data do you need to store for like an hour, we'll say, in your tests?
Yeah, well, it depends on how busy the network is, and how many of these OpenFlow messages are exchanged. If it is OpenFlow, now, and I did mention OpenFlow a lot in my slides, but I just want to make the point that, this can apply to other control plane protocols. So OpenFlow is very chatty, and it does result in a lot of messages, but they're small enough. It isn't. I'd have to look up what the actual figures are. I did do some kind of analysis of that for the one of the papers back along the way, but you're saying running it for an hour, that there'd be no storage issue for that. I was looking at, well, what if it was a data center network, a busy data center network, and you need to store logs that cover months or years, and then we were getting into kind of terabytes of storage.
Okay. But yeah, still, I suppose it's still kind of normal for.
Yeah, exactly. Terabytes, that's still achievable.
That's perfect. Thanks.
Yeah, no problem. Just to kind of say a bit more about the security. Clearly, that wasn't my focus in what I was doing, and it would take a bit of a review of that to say, well, are all the requirements there? But absolutely, your suggestion of if you have a bit of malware running and maybe things are happening a bit too quickly to watch in real time as it's happening. But if you've recorded everything, well, for me at the control plane, then you can analyze that afterwards very closely and maybe run some queries to get useful information out of.
Absolutely. Thanks.
Yeah.
In terms of, so like you said, it can be used for administrator querying the network. So like, can it be used like to kind of enforce service level agreements and that kind of querying, or
that would be a part of the intention, all right, because I did mention, well, I probably mentioned compliance, but yeah, even for one of the things that I thought about was for a data center operator that has service level agreements with clients, and the clients are kind of questioning it and saying, well, look, as far as we could tell, these two hosts couldn't communicate last Tuesday at 3 o'clock, and the data center operator could go back and query and either be able to say, well, everything was in place. I can prove that everything was in place for that communication to happen, or actually, you're right, there was a problem. The rules weren't there, or there was a link failure or something. I'm going to look at it more closely and possibly make sure it doesn't happen again, or try and come up with some way of mitigating the chance of it happening again, or the impact of it happening again in the future.
Okay. That's great, Jonathan. Cheers. Any more questions?
Yeah, I had a question, Victor. So, Jonathan, like, did you look at how quickly it takes to build a model, and how quickly your model reacts to changes in the network?
The length of time, I suppose, the length of time to populate the model, isn't it? To populate the message ontology with the OpenFlow messages, and then the time to infer. And the code that I've written, I suppose it is kind of prototype code. It isn't optimized, and it does take quite a while to run. Not so much for populating the message ontology, but the the code to infer the instances. Some of that can take could take hours to run, to be honest. With this network, which is a reasonably sized data center network with 12 PCs, or sorry, 12 switches and 120 hosts. It's certainly not a hyperscale network, but it's a reasonably sized data center network. So the inference code can take quite a while to run. Again, depending on how busy, how many messages have to be processed in order to do the inference. But like I say, it isn't optimized at all, and in particular, the Lisp code seems to run quite slowly.
Which is, well, fair play to you for writing Lisp code in first
instance. It was an adventure.
Yeah, but if there's a change, so let's say that you've populated the got your ontology, and then there's a change in the network, such as a switch goes down. How long does it take for that event to be reflected in the ontology?
Well, you see, the ontology isn't populated kind of real time. It's not an online system. Mm-hmm. You record the OpenFlow messages and you store them, and then at some point you decide, yeah, I'm going to take that log and I'm going to populate the OpenFlow message ontology with it and infer all the instances.
All right. I understand.
So it is meant to be used offline.
All right, I see. Okay.
But, yeah, no, an online system would be nice, all right, but that's another PhD's work.
Yeah. Thanks.
No problem.